Have you ever wondered why what goes up must come down? What keeps us grounded on Earth and prevents us from floating away? The answer lies in a fundamental force that governs the universe: gravity. Though invisible to the naked eye, its effects are felt everywhere, shaping the cosmos from the largest galaxies down to the smallest particles. In simple terms, gravity is the force of attraction between any two objects with mass. The more massive an object, the stronger its gravitational pull. This force is what holds us to the Earth, dictates the motion of planets around the Sun, and even determines the structure of galaxies across the vast expanse of space. Without gravity, our universe would be a vastly different place, devoid of the stars, planets, and even life itself that we know and cherish. It's a force that has fascinated scientists and philosophers for centuries, and its story is one of groundbreaking discoveries, revolutionary theories, and enduring mysteries that continue to captivate our imagination. The story of gravity is often linked to a falling apple and a brilliant mind, Sir Isaac Newton. Legend has it that while sitting under an apple tree, Newton observed an apple falling to the ground. This seemingly simple event sparked a profound question in his mind: what force pulled the apple towards the Earth? This question led Newton to formulate his law of universal gravitation, a groundbreaking theory that revolutionized our understanding of the universe. Published in 1687, Newton's law states that every object in the universe attracts every other object with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. In simpler terms, this means that objects with more mass exert a stronger gravitational pull, and the force of gravity weakens as objects get farther apart. Newton's law provided a mathematical framework to explain a wide range of phenomena, from the falling of objects on Earth to the movement of celestial bodies. It allowed us to understand why the Moon orbits the Earth, why planets revolve around the Sun, and even helped predict the existence of Neptune, a planet discovered based on its gravitational influence on Uranus. Gravity's influence is all around us, shaping our everyday experiences in countless ways. From the simple act of walking to the ebb and flow of ocean tides, we are constantly interacting with this invisible force. One of the most obvious examples is the way objects fall to the ground when dropped. Whether it's an apple falling from a tree or a ball rolling off a table, gravity pulls these objects towards the center of the Earth. The acceleration due to gravity is constant for all objects, regardless of their mass. This means that a feather and a bowling ball, if dropped in a vacuum where air resistance is negligible, would fall at the same rate and hit the ground simultaneously. Another fascinating example of gravity at work is the phenomenon of tides. The gravitational pull of the Moon and, to a lesser extent, the Sun on Earth's oceans causes them to bulge outward on opposite sides of the planet. These bulges create high tides. As the Earth rotates, different locations experience these tidal bulges, resulting in the regular rise and fall of sea levels. Tides are a powerful demonstration of how gravity from distant celestial bodies can have a tangible impact on our planet. Gravity's influence extends far beyond our planet, orchestrating the cosmic dance of celestial objects across the vast expanse of space. It is the force that governs the motion of planets, stars, and galaxies, holding them in their intricate orbits and shaping the large-scale structure of the universe. Planets, including our own Earth, orbit stars due to the gravitational attraction between them. The star's massive gravitational pull keeps the planets in their elliptical paths, preventing them from flying off into the vastness of space. Similarly, stars themselves are not randomly scattered throughout space, but are often found in gigantic clusters called galaxies. Hundreds of billions of stars, bound together by their mutual gravitational attraction, orbit a common center of mass within a galaxy. Our own Milky Way galaxy, a barred spiral galaxy containing billions of stars, is a stunning example of gravity's organizing power on a cosmic scale. Section 5. Beyond Newton. Einstein's revolutionary insights on gravity. While Newton's law of gravitation provided a remarkably accurate description of gravity, it wasn't until the early 20th century that Albert Einstein revolutionized our understanding of this fundamental force. Einstein's theory of general relativity, published in 1915, proposed a radically different view of gravity, not as a force acting across space, but as a consequence of the curvature of space-time itself. According to Einstein, massive objects like planets and stars warp the fabric of space-time around them, much like a bowling ball placed on a trampoline would create a dip in the fabric. This curvature of space-time is what we perceive as gravity. Objects moving through space-time follow the curves created by massive objects, just as a marble rolling on the trampoline would spiral towards the bowling ball. Einstein's theory provided a more complete and accurate description of gravity, explaining phenomena that Newton's theory could not, such as the bending of light around massive objects and the subtle shifts in the orbits of planets. Section 6: Black Holes, Gravity's Ultimate Triumph. One of the most fascinating predictions of Einstein's general relativity is the existence of black holes, objects of such immense density and gravitational pull that nothing, not even light, can escape their grasp. Black holes form when massive stars collapse at the end of their lives, their matter compressed into an infinitely small point called a singularity. The gravitational pull of a black hole is so strong that it creates a region of space-time around it called an event horizon. Anything that crosses the event horizon, including light, is trapped forever, unable to escape the black hole's gravitational clutches. Black holes are among the most mysterious and intriguing objects in the universe, and their study continues to push the boundaries of our understanding of gravity and the nature of space-time itself. Section 7: Harnessing Gravity, from Satellites to Renewable Energy. Gravity's influence is not limited to the realm of astronomy and physics. It plays a crucial role in various technological advancements, and even in our quest for renewable energy sources. One of the most prominent examples is the use of satellites for communication, navigation, and Earth observation. Satellites are launched into orbit around Earth, where they are held in place by Earth's gravitational pull. By carefully calculating the satellite's speed and trajectory, we can ensure that it maintains a stable orbit and performs its designated functions. Gravity also plays a vital role in harnessing renewable energy sources like hydroelectric power. Hydroelectric dams utilize the gravitational potential energy of water stored at higher elevations. As water flows downhill, its potential energy is converted into kinetic energy, which is then used to turn turbines and generate electricity. Understanding gravity is essential for designing efficient dams and maximizing energy production from this renewable source. Section 8: Unraveling the Mysteries, the Quest for a Unified Theory. Despite centuries of study and groundbreaking discoveries, gravity remains one of the most enigmatic forces in the universe. While we have made significant strides in understanding its nature and effects, many mysteries still surround this fundamental force. One of the biggest challenges in modern physics is to reconcile gravity with the other fundamental forces of nature: electromagnetism, the weak nuclear force, and the strong nuclear force. These forces are described by quantum mechanics, which governs the behavior of matter and energy at the atomic and subatomic levels. However, attempts to unify gravity with quantum mechanics have so far proven unsuccessful. The quest for a unified theory of everything, one that can explain all four fundamental forces within a single coherent framework, is one of the most ambitious goals of modern physics, and gravity holds the key to unlocking this grand unification. Section 9: Gravity's Enduring Allure, Inspiring Curiosity and Exploration. Gravity's enduring allure stems not only from its profound influence on the universe, but also from its ability to inspire curiosity and drive scientific exploration. From the ancient Greeks who pondered the nature of falling objects to modern-day physicists grappling with the mysteries of black holes, gravity has captivated the human imagination for centuries. It is a force that connects us to the cosmos, reminding us that we are part of a much grander tapestry, governed by laws that transcend our everyday experiences. As we continue to explore the universe, from the depths of black holes to the farthest reaches of space, gravity will undoubtedly continue to guide our journey, revealing new wonders and challenging our understanding of the cosmos we inhabit.